Well, welcome everybody to the Sol Speaker Series. I can't believe this is our seventh one this year. And I've been looking forward to this talk tonight for some time. I'm Captain Barb Barton. I'm the Director of Starfleet Sciences. And our guest speaker tonight is Dr. Matthew Szydagis. He is an associate professor at SUNY at Albany. And I practice this all day, and I would challenge anybody to say this three times fast. He is an experimental astroparticle physicist. Okay, everybody ready to say it three times fast? He's an experimental astroparticle physicist. Good, good. He specializes in and focuses on dark matter and UFOs. And he's also been on the History Channel, and he's a regular expert there for the program The Proof is Out There. And he's going to be talking tonight about space and time travel, models for that, and can it work? So, welcome to you, Dr. Szydagis, and thank you so much for being here today.
Thank you so much for having me. Thank you for the invitation.
Sure.
So I'm really excited to be here and to talk to a fellow Star Trek fan. I'm a lifelong Star Trek fan. Literally, like as far as I can remember, I think I've been watching Star Trek since I was five, maybe 4 years old, even. Um, So, what I'm going to talk to you all about tonight over the next roughly 45 minutes, and hopefully then plenty of time for questions, is I'm going to be telling you about what real science and what real engineering exists and might work one day for allowing space-time travel. And I threw those two together because space travel is always time travel, and time travel is always space travel because space-time continuum. So every spaceship is a time machine, and any time machine would have to be a spaceship. So I'm going to be talking about a lot of separate but interrelated things because there's still, of course, even though space and time are connected, we can still think about um, separate issues of crossing interstellar distances for space travel and the issues of editing the past if that's ever going to be possible. So I'm going to share my screen now because I have a PowerPoint presentation for you all tonight. But I do hope I get lots of questions that we have some interactivity also. So here are some. This is a picture of me sitting in the captain's chair. So if those of you who are not familiar with this, in Ticonderoga, New York, which is only a couple hours north of me, there is a complete 110% accurate replica of the original series set in every aspect. It's not just the bridge, it's the bridge, engineering, sick bay, captain's quarters, conference room, literally any room you've ever seen on the series, auxiliary control, even like anything you've seen, they have a complete replica and you can take tours and you get to actually sit in the captain's chair. And it's not expensive, actually. It's not Las Vegas. It's middle of nowhere in New York, not reachable by airplane. Nearest airports are many hours away. Is the best kept secret of New York State. And since we're going to be talking about time travel, in addition to space travel, I've got Back to the Future here and this famous 1912 painting, and of course a clip from the City on the Edge of Forever, The Guardian of Forever. So if you've seen my talk already, I have a TEDx talk on YouTube about time travel. You'll definitely still learn something new because, as I said, I'm covering both space and time travel today. So here are a few more pictures. This is when I visited Riverside, Iowa, future birthplace of Captain James C. Kirk. This is me with my daughter Ella, and this was on my way when I was moving from California to New York. We drove through Riverside, Iowa, You know, future birthplace of Kirk in the prime timeline, of course, the better timeline, of course, in my opinion. And then here's a picture of me. Here's where I got my picture with William Shatner. And then a friend of mine put Rigel 12 in the background. So the original background was like a boring white whatever at the venue. And I'm actually holding there an original William Shatner Captain Kirk action figure that I actually played with as a child. It's not in the package. I'm not a collector because I believe toys should be played with. I know it's a very controversial idea, but I'm not a collect. I actually take them out of the box, and I know the price immediately gets worse, but I actually play with the toys. So that was a toy that was my actual childhood Captain Kirk action figure. So I want to motivate today's topic of space and time travel with this. It's a real quote from Simon Newcomb, a Canadian mathematician. And this is not a myth. This is not a legend. You can look up, he actually said this in the early 1900s. Aerial flight is one of that class of problems with which men will never have to cope. And he went on to talk about how impossible air travel is. And there are countless examples of this in history. There is the example where a couple weeks before the launch of Sputnik, a British astronomer said, space travel is nonsense. It will never work. It's impossible. The New York Times published numerous editorials about how air travel will never happen or it'll take millions of years. So actually, the New York Times editorial on air travel was published literally 2 days 2 days before Wilbur and Orville's first flight. They published an article saying that it will take humanity millions of years to figure out how to do air travel. And so I think it's very important to keep an open mind and to only use the word impossible with extreme caution. So I'm not claiming that everything is possible. There will certainly be some limitations of the laws of physics. But to think that we, the human race in the 21st century, has already figured everything out, that is completely the height of hubris. I'll give you one more example before moving on, which is Harry Truman was told by an admiral that the atomic bomb was a waste of money, that it would never work. And this admiral said, and I speak as an expert in explosives. Again, a real quote. This is not a myth. This is documented. So it's important to keep an open mind on what's possible. Now, when I talk about time travel today, though, I'm going to talk about the literal fun kind, the science fiction kind. Not like, oh, why does suffering mean time goes longer? I don't care. Frankly, I'm not a neuropsychologist. I'm like, that's cool, but I'm talking real time travel, not like, oh, can you do it in the mind? No. I mean the real deal. So one of our foundational models that allows us for the possibility of time travel is Einstein's theory of special relativity. And this animation here is going to illustrate one of its fundamental principles. And it's very important to keep in mind is that when I say the theory of special relativity, the word theory in science means something the opposite of what it means for everyone else. In science, the word theory means extremely well-established fact. That's the opposite of what the word means for everyone else. So you'd have to be, it's insane to doubt Einstein's theory of relativity that's been confirmed so many times and reconfirmed and rechecked, and our technology relies on it. So when I say the theory of relativity, if it makes you feel better, replace the word theory with fact in your mind. Now, of course, there's things like string theory, which we don't talk about, which just muddies the waters. It uses the word theory improperly and incorrectly because there's zero evidence for string theory. So, but the theory of relativity is about as rock solid as something that humanity can understand. It's like atomic theory, theory of evolution, and things like that are just established extremely well. So Einstein came to a very profound epiphany, a realization, one of many. But the one I'm talking about on this slide is related to something called a light clock, which doesn't actually exist. This was a thought experiment, which then led to real theories and models that led to real experiments. But this initial step was what's called a Gedanken experiment in German, a thought experiment. So imagine that you have light traveling between two mirrors separated by a height h, and the tick and the tock of the clock are the photon bouncing off of each mirror. Now, here is where things get interesting. Now, imagine that the mirror is moving. If the mirror is moving, now the light has to travel a longer distance to an external observer. And in Newtonian mechanics, this isn't a problem. If instead of light, this red thing is a ball, that's not a problem. We say that the ball is traveling faster. From the external perspective, there's a horizontal and a vertical velocity, and we add them in quadrature, and we use the Pythagorean theorem, we use trigonometry. But the problem is that Einstein discovered, or rather postulated, that the speed of light is constant in all frames of reference in order to reconcile Galilean and Newtonian mechanics, classical mechanics, with electromagnetism. But if the speed of light is constant in all frames of reference, there are some very deep and serious mathematical consequences. So in this example, if light behaved like everything else in the universe, we would just say, oh, no problem, the light is traveling, at a faster speed to the external observer because you have to add the vertical and the horizontal components of the speed. You can't do that for light because it's the same speed in all frames of reference. We don't know why. That's just how the universe is. And it's the only way to reconcile classical mechanics and electromagnetism. Again, two theories we know are both very correct. And so, but are contradictory. But if the speed of light is constant, what happens when the light is traveling this diagonal path, this hypotenuse? That means it's going a longer distance. Velocity is equal to distance over time. So the only way for the velocity to be the same, and with the distance being greater, would mean that the time is greater. So what does that mean? That means that time slows down for moving clocks. And it's deeper than that. It has nothing to do with clocks. It has nothing to do with this particular clock. It's literally time itself on a fundamental philosophical level. This is not about biology. This is not about technology. It's on a deep and fundamental level. So what this leads is to something called the twin paradox, which is not a paradox. It's only a paradox if you don't understand the math in relativity. There's no paradox whatsoever. So a better name for this would be the twin effect, and that's what I try calling it more often. So in the twin effect, if I have two twins and one takes an interstellar journey, turns around and comes back, the one that stayed behind on Earth will be older. And again, this is not a theory the way that's used in colloquial speak. This is scientific fact. We do this every day. We don't have the technology to do it with people, but we do it with subatomic particles on a daily basis, and we've been doing so for decades. So we use the twin effect all the time. This is called relativistic time dilation. So we do this every day. At the particle accelerators like the Large Hadron Collider, particles are created that are radioactive, that are short-lived. But if they're traveling near the speed of light, they live longer than they're supposed to. And then they would in a rest frame of reference. Another effect beyond the time dilation effect is there's also a length contraction effect and also a Doppler shift. And so instead of change in sound or change in pitch, like you have Doppler effect for sound, the Doppler effect of light is a change in color. And I use the term color loosely. Infrared, X-ray, gamma ray, ultraviolet, those are all colors. Just because humans can't see them doesn't mean they're not colors. Same thing, infrared, radar. There are aliens out there, I'm sure of it, who would see Wi-Fi, who would see your wireless internet signal bouncing around your house, and it would drive them crazy. So when I say color, I mean when something is Doppler shifted, it can shift out of the human visible range. And that's important. We're going to come back to that effect because that's going to have some consequences, including some negative consequences for interstellar travel. But the time consequence is a positive one, as we'll talk about next. So this is an illustration. I've adapted these from a presentation of a colleague of mine, Professor Kevin Knuth, also at UAlbany. And as I grew up with TNG, I love this example because it's Enterprise D and a starbase. And so when you are traveling, and again, we're talking only slower than the speed of light now. We have not gotten to faster. That's later in my talk. I want to illustrate for you now with nice Star Trek animations from my friend Kevin what time dilation looks like and length contraction. So if I'm stationary and I observe a ship going by that's traveling near the speed of light, it will appear contracted and its time will appear to go slower. But there are dual perspectives. Those in the galaxy see the ship's clock moving slowly, but the ship traverses the galaxy in a short amount of time according to ship clocks. So if I'm in the ship, the distance across the galaxy is shortened and the time it takes to do so is shortened. So space travel is time travel. So for those in the galaxy, the time elapsed for the ship to traverse the galaxy is over 100,000 years because the galaxy is over 100,000 light years across. But from the ship's perspective, if I'm going 0.9999999 times the speed of light, I can cross the galaxy in a few months, few weeks even. So in fact, this is one of my biggest smart aleck Star Trek corrections ever is Star Trek Voyager. This always irked me all the way from season 1 is I thought to myself, man, Captain Janeway, she used to be a science officer, so why doesn't she know this? We've known this since 1905. So this isn't new. Even in the 21st century, this is over 100 years old. If I was Janeway, I would say, forget the warp engines, turn on the impulse. We'll get to Earth in a few months. But now everybody's dead because it's hundreds of thousands of years later. No problem. Let's just do a slingshot like Captain Kirk did. Done. Of course, then you wouldn't have 7 seasons of Stuck in the Delta Quadrant. But that's my smart aleck, scientifically accurate solution of Voyager is shut off the warp, gun the impulse, make it back to Earth in a few months, and then just cheat with time travel to the past if you want to get back to your present. So yeah, biggest plot hole ever in Star Trek is actually literally the entire plot of Voyager, because science fiction, not just Star Trek, science fiction always forgets time dilation. And it's one of my biggest pet peeves as a scientist because we've known this since 1905. So this is extremely old news. This should be old news to everybody. We should all be learning this in 6th or 7th grade, and it should be extremely old news. And be like, oh yeah, time dilation, of course. And so it is a myth that interstellar distances are just too hard and we'll never cross them, or it'll take too long. That's all garbage. That's all nonsense. And we've known that's nonsense since 1905 because time dilation actually helps you. So actually, you don't even need warp drive to explore the universe. It's completely unnecessary. So if warp drive is never possible, it's never invented, irrelevant. Doesn't matter because time dilation helps you. All you need to go slower than the speed of light, and you can traverse the entire universe. So this time dilation effect is shown here graphically. It's nonlinear, and the closer you get to the speed of light, the more the difference in time is. And the length contraction is also another way of looking at it. And an example that I give my students is, and this is relevant, again to especially to the original series, as well as one of the TNG season 1 episodes where they visit the Andromeda Galaxy. You might have heard that it would take 2.6 million years to reach the Andromeda Galaxy. And that's false. If I traveled just 0.06 meters per second, slower than the speed of light, I would reach the Andromeda Galaxy in 50 years. 50 years. That's it. Yes, 2.6 million years will have elapsed on Earth, but who cares? There are plenty of examples, even from human history, of nomadic civilizations. So as long as an alien race is willing to become nomadic and not care about having a home planet, the entire universe is your oyster. You can literally get to Andromeda in 50 years. So again, another smart Alex Star Trek answer from me. If I was the Calvins in the original series, I would need to modify the warp drive. I'd be like, that's a huge waste of time, 300 years. Again, let's just let's put the impulse engines to maximum and rely on time dilation. Now, you're probably thinking by now, but there's got to be a catch here. There has to be. Why haven't we done this yet? And there is a catch. But the catch is not it's not a physics one. It's a technological one. So the one catch is that your mass, your apparent mass, increases as you approach the speed of light. Now, I'm not talking about gravity. You don't attract things suddenly because you're as heavy as the Earth. Not talking about gravitational mass. I'm talking about inertial mass, which when you're sitting at rest, those are, of course, the same thing. Not talking about gravitational mass, and I'm not talking about the amount of stuff inside of you. As you approach the speed of light, it's not like there's more stuff inside of you. It's not what I mean either. Basically, this is due to the shift in energy of the potential energies of all the atoms and molecules in your body. But the huge problem here is we can't then approach the speed of light with a massive object, let's say like a multi-megaton spaceship, starship, because it would take more fuel than we currently have the technology to deal with. That doesn't mean it's impossible. It just means it's extremely hard. But given 50, 100 years, 1,000 years, if humanity doesn't blow itself up first, of course, this should be a solvable problem. And if there are species out there that have lived for thousands, millions, billions of years earlier than humans, there's zero doubt in my mind this has been figured out already by somebody out there has already figured this out, because the problem here is fuel. If you accelerate at 9.8 meters per second squared, which is very comfortable, right? That's 1 g. If you accelerate for 9.1 meters per second squared for 2 or 3 years, you're pretty much at the speed of light. You're at 0.9999 speed of light. And so the problem is the amount of fuel you need would constantly increase with time. So the problem is not solved. The problem is not solved. Now, there are these hypothetical particles that we know Star Trek fans call tachyons that have negative mass. And instead of this problem, they have the opposite problem, which is they're always traveling faster than the speed of light and they can't slow down. And in fact, when they lose energy, they actually go faster. They're backwards because they have negative rest mass, which is really strange. We have no evidence they exist, though, and if they did exist, they're always traveling back in time, so they'd probably all pile up at the Big Bang and be useless to us anyway. So unfortunately, tachyons are not a helpful solution either for space travel or for time travel, because they probably don't exist, and if they do, they'd be very hard to harness. But does that mean the book is closed? Absolutely not, because if we could crack the fuel problem and the propellant problem, the shielding problem, this should be solvable. Now, everyone always still goes back to faster than light because we just have this visceral reaction against time dilation. We don't believe it at a visceral level the same way we know the Earth goes around the sun and not the other way around. We just, maybe because 1905 is really not that long ago, we have a visceral reaction of disbelief, even though it's been proven 10 million times now. And so we always want warp drive. The only benefit of warp drive, there's only one, which is you can make it back home in time for dinner instead of your civilization being dead for countless thousands of centuries or millennia. But personally, I don't care. I'd love to be an explorer. So that not being able to make it back home to Earth is not a problem. But for many people, it is. So everyone wants warp drive. There's good news on this front, which is there's been an explosion of ideas. And everyone always talks about the Alcubierre warp drive, which is an idea from the 1990s. Now, that's a seminal. Miguel Alcubierre was the first one to come up with this idea. However, most people know his name and don't know a single of these other names. So Alcubierre was the most important name here. He's the first. But his work was wrong because he didn't have a fancy three-dimensional spaceship like in this cartoon. He assumed a zero-dimensional point-like particle traveling in 1D. Our world is not one-dimensional. It's three-dimensional plus time. And real spaceships aren't smaller than atoms. And so these other authors who came later, these other scientists, improved upon Alcubierre's work and made it more realistic. We've got Notario, Van de Broek, Hal Puthoff, Eric Davis, Travis Taylor, more recently Eric Lenz, and Lavinia Heisenberg. I don't know if she's related to the Heisenberg. Actually, I'm uncertain about it. Then we've got Bobrick and Mateer, and any of these people are potentially real life Zephram Cochranes who are on the case and working this out. So the fundamental idea here is very different from the relativistic travel we've talked about so far, where we're trying to still do a traditional rocket or fuel or propellant to try to get us up to the speed of light. Trick here is you actually warp space-time. And so actually when Star Trek came up with the phrase, warp drive in the original series, Star Trek, the original series, was 3 decades ahead of its time. Way ahead of its time, because until the 1990s, with the work of Dr. Miguel Alcubierre, it was just nonsense, right? Technobabble. But it turns out warp drive is the correct term, because if this works, if you could warp space-time, this is the one workaround for getting around the speed of light as being the maximum speed limit in the universe, because there's an exception to the speed of light being the maximum speed limit, which is space itself can expand and contract faster than the speed of light. There is no rule that says it can't, and in fact it does, and it has been since the Big Bang in a violent way right after the Big Bang in the inflationary period. And so you're not actually moving. The spaceship is stationary. You don't even need inertial dampers in a real warp drive. Unlike in Star Trek, you're in 0G, so I guess maybe you want some artificial gravity if you don't float around, but you're not experiencing acceleration. Instead, you're just moving space. And it was a facepalm, a moment for me in the J.J. Abrams 2009 movie when Scotty says to Spock, "Oh, I never thought of it as space moving," and I facepalm. I'm like, the real Scotty would have known that, because that's how warp drive works. That's how it works since the 1966 series, which was way ahead of its time. Now, there are much even worse catches, though, with warp drive than with relativistic travel, because unlike relativistic travel, where I'm and many scientists like me are 100% convinced we're going to make it past these problems. These are not physics problems, they're engineering problems, like the mass increase. This, though, warp drive, unfortunately might never work. And the reason is because even though I said there's an exception to the speed of light with warping of space-time, the problem is to warp space-time, you need negative energy. Something like tachyons, as I said, or something else like that. We don't know if such things exist, and we wouldn't even know how to harness them and get enough. So it's very, very improbable, not impossible, but very unlikely we'll ever be able to have faster than light travel. But you shouldn't be disappointed, because that's why I just spent the last few slides explaining it's not important. Faster than light travel is cool, but it could be impossible, and we're still safe. So it doesn't matter. We're good. But it would be fun, of course. It would certainly be fun to, go to Alpha Centauri and come back, in time for dinner, instead of it being at least 4 years later or more on Earth in the Alpha Centauri example. So we don't know how to do this warping, because one edge of this warping, the expansion part of space, we don't know how to do that without something that has an anti-gravity, a negative gravity-like effect. And as far as we know, nothing like that exists. And even worse than that, we don't even have a single theory that says that. So there is a way to go faster than light that works. We've known about it since the 1930s, but it's not real. It's a trick. And this is called turn-off radiation. And this is a this is when you go faster than the phase velocity of light in a medium, like glass or water, but it's a trick. This doesn't really count, because you still can't exceed the speed of light in vacuum unless you do the space-time warping. Nevertheless,
I think this is pretty cool. So I'm going to play this video in case of people have never seen this before. This is real. This is from a nuclear reactor turning on where the particles, mostly I think it's the beta electrons, are traveling faster than the speed of light in the water. And so what Cherenkov radiation is, it's nature's way of correcting the problem. Basically, the blue light that's emitted that you'll see, it says, whoa, you can't do that. And it slows the particles down to below the speed of light in that medium. And so here's a really cool video of a countdown of a nuclear reactor turning on. So you just witnessed you just you just witnessed subatomic particles traveling faster than the speed of light in water. And I've seen this in person because when I was at UC Davis many years ago, before I was at UAlbany, they had a reactor on campus. So I actually got to play with it and actually do science with it. That was a long time ago. So I've actually experienced this in real life. And it always made me excited that on Next Generation, at least, and in the TNG movies, they do this blue flash, especially with the Enterprise D, because I thought that's cool because it's almost like they're doing an homage to Cherenkov radiation, even though, again, it doesn't work in outer space, but in a medium like water. But I thought that was really cool. Now, I said earlier that the speed of light is fixed. So actually, there's another catch to the Cherenkov radiation. It's always taught incorrectly. Even I just did it incorrectly because it's easier to say it that way. I'm like, oh, the speed of light is slower in water. That's actually false. It's the same everywhere. Doesn't matter if it's water, glass, air. It's always travel. Its light is always going 299,792,458 meters per second. But what happens in materials is that it scatters. And if you average over that zigzagging, the average creates the illusion of slower than light. But that illusion is more than an illusion because it does lead to the real effect of Cherenkov radiation. So, oh, I didn't mean to click play again. There we go. So now let's delve a little deeper into special relativity. So Cherenkov radiation is one of the consequences of special relativity, and space-time warping is something we get from Einstein's more generalized theory, general relativity. And in the general theory of relativity, which we already got a taste of with the Alcubierre warp drive, we also want to think about, is there a possible way to time travel? And so we talked about space travel already, and now I'm going to transition a bit more into time travel for the rest of my talk, and we'll also come back to some space travel aspects. But I mentioned how in time dilation, as you approach the speed of light, what happens? Time slows down. If you could exceed the speed of light, time will go backwards. So cue the music from The Naked Time when Spock does the cold start of the engines, the da 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 da. So if you could exceed the speed of light, I'm talking about without space-time warping. I'm talking about literally exceed the speed of light in space. So not cheating with space-time warping. That does not give you time travel. It gives you warp drive, but not necessarily time travel. But if you could actually exceed the speed of light in space without cheating with space-time warping, that's not only good for interstellar travel, it also means you can travel through time. So in this diagram on the left, this is known as a light cone diagram. It's a type of diagram in Einstein's theory of relativity where the present is this surface. So that red point is one location, and this dark blue surface here represents the entire universe at one moment in time. Because, I can't draw a four-dimensional picture, so there's this 2+1 simplification here. And so this represents the entire universe of one snapshot in time, which is also a simplification because the universe, there's no such thing as the present for everybody because of time dilation. But in a local area, you can define what's called the hypersurface of the present. And this represents the future, and this represents the past, these two cones at 45 degrees. Anything outside cannot affect something in here. So, for example, if you're wondering what's happening right now in an alien classroom in the Andromeda galaxy, that's not a valid question. It's not a valid question because you cannot sync your clock between here and Andromeda because it's outside of our light. So if you could travel or signal faster than the speed of light, then you could break out of these light cones, which another term for is the causality horizon. So a cause inside the cone cannot have an effect outside it, and vice versa. But if you could go larger than 45 degrees, let's say you're a tachyon, you travel faster than the speed of light, then what could happen is you can tilt your light cone over and you can go to the past. So anything outside of these cones here represents the ability to travel faster than the speed of light. But the problem is, without the space-time warping, you can't do that because your mass would increase, and at the speed of light, your mass becomes infinite. So even all the fuel in the universe would not be enough to get you up to the speed of light, let alone to exceed it. But what if the universe itself has some weird properties? So the famous mathematician Gödel, who's infamous for his incompleteness theorem, the mathematicians kicked him out of math and said, we don't like you. We don't like this incompleteness business. Why don't you go work on Einstein's theory of relativity? Do something safe. And what did he do is he immediately broke Einstein's theory of relativity by coming up with this concept for a universe on the right, where you have a rotating universe where if you travel far enough away and come back, you could return to your origin before you left. And that's because space and time are coupled. So if the universe were rotating, it wouldn't just be space that's rotating, it's time. Now, if you ask me what's the universe rotating around, again, unanswerable question, invalid question, because it's not picturable by the human mind, but it's picturable mathematically. Now, the downside is, unfortunately, our best data shows the universe is probably not rotating. We would have seen evidence of it in the cosmic background radiation. We'd see some swirly patterns. So the universe is probably not rotating. So we can't time travel or space travel by using the universe to drag us around for free. However, we could try to construct something called a Tipler cylinder or a von Stockham cylinder. The idea here is you have a long cylinder made of a very dense material. And if you orbit it, and here I have the TARDIS because I don't just like Star Trek, I also like Star Wars and Doctor Who. I don't discriminate, and I'm an equal opportunity, diverse absorber of science fiction. So in this nice Doctor Who cartoon here shows, if you loop around the Tipler cylinder with the correct trajectory, you can travel to the path. And the idea here is that going 360 degrees in space is not the same as going 360 degrees in time. And a good analogy of this is a spiral staircase, right? We all learn that if you walk in a circle, if you walk 360 degrees, you come back to the same point. That is false. Try that on a spiral staircase, and you're really corkscrewing up to a different landing. And so there's always these exceptions. And so the idea here is that space-time is twisting around the Tipler cylinder the same way that it is in a naturally occurring rotating universe. So we can imagine some advanced civilization might build a time machine, which is a really long cylinder like this. Unfortunately, there's a catch. Yeah, there's always a catch, unfortunately. The catch is it doesn't work unless the cylinder is infinitely long or the cylinder spins faster than the speed of light. So neither of those are going to happen. And so as a result, this doesn't actually work. Now, if the universe is not infinite, then the cylinder doesn't have to be infinite. It just has to be the size of the universe, but still laughably impossible. So even if you made the cylinder out of neutronium, like the Doomsday Machine, it wouldn't be good enough unless it was infinitely long or spinning faster than the speed of light or both. So this isn't going to work either. So this isn't going to work for. So we can't exceed the speed of light by brute force to time travel or to do interstellar travel, and we can't use a Tipler cylinder or von Stockham cylinder. What about cosmic strings or black holes? I put them on the same slide because they're actually very intimately related. Because you can think of a cosmic string as a one-dimensional black hole, where instead of a point, it's a line. But unlike in the Star Trek Next Generation episode where they talked about a cosmic string fragment, no. There's no fragment. That's impossible. A cosmic string would be infinitely long if they exist. We haven't seen any evidence of them. It'd be really cool if they did. So first, a black hole, the thing that we absolutely know for sure exists. We've detected them so many times now. We've detected gravitational waves from two black holes merging into one. So if a star has sufficient mass, our sun does not. But if a star that's about 2 to 3 times massive than our sun collapses, it will collapse ultimately to a 0-degree point, which is not literally a hole. Even though we have diagrams like this, it's actually not a hole. It's a 0-dimensional point in 3-dimensional space surrounded by a 3-dimensional sphere or ellipse of the event horizon, which is the mathematical point of no return. Because the escape velocity equals the speed of light at the event horizon. So if you can't go faster than light, and that also aggravated me about the J.J. Abrams 2009 movie where they're at warp speed and they can't escape the black hole. And I'm like, you're at warp speed. You are fine. And I was like, wanted to scream at J.J. Abrams and at the movie, because if you could go faster than light, then you're fine with a black hole. So black holes, if they exist, will allow time travel, but not to the past, unfortunately, to the future. So it's like a shortcut of the time dilation from speed. So if I orbit let's say there was a black hole not too far away. It was accessible, let's say, by humans, not too far outside of our solar system. You could go orbit a black hole for a few months, come back, and several million years have elapsed on Earth. And that's because strong gravity also slows down time, just like high speed. But unfortunately, just like high speed, it's a one-way ticket to the future. It's not a way to get to the past. But if cosmic strings existed, these one-dimensional black holes, and there are several ways they could have been formed in the early universe or between collisions between parallel universes, like in the alternative. Basically, if cosmic strings exist and you had two of them really close together and you did a figure eight around them, bam, you could time travel to the past. No catches. That's the best way. The problem is we don't know if cosmic strings exist. They might not exist at all. Black holes for sure do. Cosmic strings only exist under very particular hypotheses and models. Now, what if instead of warping space, like black holes and cosmic strings, why did they work for time travel in this case? Not for space travel, but for time, because they warp space in a natural way, just like a rotating universe does, or a Tipler cylinder does in a artificial way. Now, what if we forget about warping space? Let's punch a hole through space. And so the classic example of that is the wormhole. And the idea with a wormhole is that the analogy is imperfect. Our analogies are imperfect. So we pretend wormholes are two-dimensional. That's not the case. So a real wormhole would probably look like the one in the movie Interstellar. It probably would not look like the Bajoran wormhole in Deep Space Nine, which was a circle, which again is a misunderstanding of this diagram, because this diagram is not meant to be literal. It's an analogy where you imagine you have a sheet of paper and you bend it, and we've all done this, I'm sure, and you stick a pencil between and ta-da, this is our analogy for a wormhole. Now, what's really cool about wormholes actually is it doesn't require extra dimensions. So when we imagine wormholes, we think, oh, we're going through hyperspace or some extra dimension. Actually, and I'm a scientist, and I only learned this myself 3 years ago. I had been thinking about this wrong for decades. You don't need an extra dimension. That's just to make it easier to visualize for humans. If there are no extra dimensions, wormholes could still exist. It just means that, like, imagine a blackboard, and I draw a circle on one part of the blackboard, a circle on the other, and I just say, those points in that circle are equivalent to the ones in the faraway one. Done. You don't need a tunnel between. So wormholes, this tunnel thing is just, it's a cute picture, but it works even without a literal extra dimension to tunnel through. So in the 2D example, the way it's drawn is this third dimension here is some, extra higher dimension that's not actually part of your main universe. So what's the catch with wormholes? Now, the thing with wormholes is we don't know how to make them stable. So even if we could invent a way, we don't even have that, but let's say we came up with a way of creating one. Let's say it takes a Planck energy particle beam or laser and two of them crossing, maybe, like crossing the streams in Ghostbusters or something. Maybe if you cross two collider beams of really high energy particles, you can make a wormhole at that crossing point. The problem is we don't know how to keep it stable. Anything entering the wormhole will collapse it, even photons. So like when Denzel Washington shines the laser pointer in the movie time travel movie Deja Vu into the wormhole, that would collapse the wormhole. Nothing can successfully make it through a wormhole except tachyons, which don't exist. So that's another problem. But if you had some sort of anti-gravity like thing or something that produces negative energy, that would let you hold the throat of the wormhole open. So I'm hopeful. I'm cautiously optimistic, but the wormhole has the same problem as the Alcubierre warp drive, which is that it requires some form of large amounts of negative energy. And when I say large amounts, I mean more than the mass of Jupiter, talking large amounts. So not only would we need massive amounts of material, we would need massive amounts of material that may or may not exist. And so it's a serious issue. But maybe that negative energy does exist. So there is some ray of hope. And that is the quantum 0-point energy, which is, again, real, which is a myth we've measured in the lab. So if you've ever heard of the Casimir effect, this is where if you take two uncharged metallic plates in a vacuum, if the spacing between them is close enough, you can get an electrical attraction between the two plates. And the reason why this happens is because even the vacuum of space isn't empty. It constantly has matter and antimatter being generated over and over again for all eternity. And this is called particle-antiparticle virtual pair production. And so you're making electrons and positrons most of the time. And so electrons and positrons, these virtual electrons and positrons, can collect on the plates and create an attraction. So the energy of the vacuum is actually negative energy because you're borrowing from zero energy from the vacuum. And so what you can create particles with negative mass and negative kinetic energy. Basically, this is not strictly correct, but the very fun way that I like to think of this is basically one way to think about quantum 0-point energy is you can break the laws of classical physics, just don't do it for too long. So you're sneaking in under Heisenberg's uncertainty principle. You can break conservation of energy, but just don't do it for too. And the longer you want to do it, the less energy, unfortunately, you get to do it with. So the Casimir effect experiments have only produced teeny tiny amounts of energy. So we have no idea how to scale this up. So even if I had two metal plates the size of, our solar system, I would have not even close to enough energy for warp drive or time travel, all those things holding wormholes open. So while there is a ray of hope here, we don't know how to scale up these quantum 0-point effects that can have negative energy like the case. But another ray of hope comes from the universe itself. We think that the same 0-point energy in the Casimir effect is also the dark and so-called dark energy in cosmology, which is driving the expansion of the universe at an accelerated rate. So just like how we looked at birds and we saw, hey, maybe we can build airplanes, right? We saw birds and we saw insects. Humanity can look to the universe and see, well, there's this naturally occurring example of negative energy, of vacuum energy. maybe we could harness it someday. The problem is that as much as the dark energy is, a lot of it in the universe, when you look at small scale, like the scale of our solar system, it's again a pathetic amount of energy. If you could harness all of the dark energy in the solar system, you could probably, I don't think you could even light a light bulb or an LED for more than a fraction of a second, let alone power your warp drive. And so while there is a ray of hope here, there's still a lot that needs to be done and a lot that needs to be understood. But the universe as a whole brings us back to the point of gravity. I mentioned earlier how gravity warps space-time. And so this is another real effect. It's like the twin effect, but for gravity instead of speed. So if this is the Willis Tower in Chicago, my hometown, if you are at the base of the tower, time goes more slowly for you than at the top. We have the technology to measure this. We've had it for 50 years. We can do it with cesium atomic clocks or with aluminum ion clocks. There are better clocks now. We now have the technology to measure the effect that I'm pointing at to you. Heck, this is better than I don't know if, I would hope the Star Trek tricorders would be able to do better than this, but we currently have the technology right now, today, to measure a difference of 1 meter on the surface of the Earth. If you are 1 meter farther away from the surface of the Earth, time goes a little bit faster, and we can measure that. So our GPS satellites, of course, have to account for this, plus the special relativistic time dilation. So why did I come back to this time dilation effect? Because it is so important for our current technology. As I said, GPS wouldn't work without accounting for this because of the Earth's gravitational well. There's the gravitational well of the sun. And when you have countless galaxies, let's say you have a cluster of thousands of galaxies, and each of those galaxies has 100 to 500 billion stars, and each of those galaxies has a supermassive black hole at its core that's millions of solar masses, that's a lot of gravity. And so gravity can bend not only time, it can bend light. And so this is an incredibly important effect in my own research on a dark matter, looking at the curvature of light due to gravity. And here's a picture of what light trapped in orbit around a black hole would look like. This is from the movie Interstellar. Now we actually have a real picture. As of a few years ago, we actually took the world's first picture of a black hole. I forgot I should add that into my talk for future versions. So I was building up with all of that to the slingshot effect, because this is one of those great things that Star Trek almost gets right. So if you slingshot around a massive body, it doesn't actually take you to the past. It's a one-way ticket to the future. So cool idea. And the principle is almost right, but it's for the future, not the past. Because if you wanted to get to the past, you need to slingshot around a negative mass or negative energy body. But the other thing that Star Trek gets wrong is actually the sun or any star is nowhere near massive enough. If you slingshot around the sun, congratulations, you are a fraction of a second into the future with time travel. Not a big effect. You need something like a black hole or a cosmic string. Nevertheless, I still, of course, love the slingshot effect. And of course, I love the Guardian of Forever episode as well, but I like to reinterpret that episode as the Guardian Forever was producing gravitational waves, and that's what was shaking the ship. And I mean, they don't use that term on the episode, but I like to give them the benefit of the doubt and say, again, they were ahead of their time by half a century when gravitational waves were actually discovered, in this case from 2 rotating black holes. But if you're experiencing gravitational waves as bad as they were on City on the Edge of the Edge of Forever, you've got problems. You've got big problems. So there is one more time travel story I have to tell you, and it connects with rotation and gravity again. This is Professor Ron Mallett of the University of Connecticut. I know him. I've talked to him. I've invited him to give a talk at my university. I've given given a talk on my work on dark matter at his university. He's the only scientist I know in real life. I know several scientists in real life who are working, on warp drive. I mentioned them earlier, exotic propulsion, even some people at NASA. He's the only scientist I know in real life that's actually trying to build a real time machine. And his idea here is it's similar in some ways to the Tipler and von Stockham cylinders. We've got the same theme of cylinders in rotation again. His idea is to create a circulating beam of light. You insert a particle on one end, and it comes out on the other end in the past. So unless you build a really, really big cylinder, this is not practical for human or ship time travel, but maybe as a time telephone. So we can call the past, warn them of upcoming tragedies or disasters or something like that. That's Ron Mallett's idea. And the idea here is that when the lasers are powerful enough, you create a swirling of space-time, just like the Earth does with its rotation, but that's a very weak effect. Just like the sun does with its rotation, very weak effect again. Just like a black hole does with its rotation, that's a strong effect, or a cosmic string. Now, probably thinking, how could we possibly do this on a tabletop? Well, lasers are not quite powerful enough yet, but they're getting there. And so lasers are not quite powerful enough to make this actually work. Some of Ron Mallett's critics claim that you would need an infinite energy of laser or an infinitely long cylinder. So the jury's still out, but I think this is one of the most practical proposals when it comes to time travel. My money is on this. And for space travel, my money is on slower than light, using time dilation. So we can't talk about time travel without talking about the paradoxes. So Polchinski's paradox is a famous paradox that is the less violent version of the grandfather paradox, which is it's the same idea, but it doesn't involve murder. So basically, the idea is you're playing pool and you hit a pool ball, let's say, into a wormhole, and the pool ball emerges in the past, hits itself in the past, prevents itself from entering the wormhole. What would happen? And there are many solutions to this that we don't know the answer because nobody's discovered time travel. Nobody knows the correct answer because we don't even know if time travel to the past is possible. But if, let's, for the sake of argument, say time travel is possible, including to the past, what would happen? So there are several ideas. The two major ones, of course, are, and Star Trek can't make up its mind. Of course, it's always changing what it does with this. One option is called Novikov's self-consistency. This is the idea that no matter how hard you try, you absolutely cannot change the past. The past is immutable. You can only fulfill it. The other possibility is something called the multiverse that, of course, they're familiar with the Star Trek fans. Well, okay, you can kill your grandfather, but the prime, he's still alive in the prime time, so it's fine. Now, another possibility illustrated here is imagine a garden of many paths, like the sci-fi story. I'm not talking about multiverse, though. There is another possible solution from quantum mechanics where if you go back in time, let's say successfully kill your grandfather, you are dead and you are alive. You are both. You have become Schrodinger's cat. What does that actually mean, though? I have no idea, and nobody else does either. Like, does that mean you don't disappear like in Back to the Future, but you don't have a driver's license or security card anymore, and you're not in any records? I don't know. I don't know what it means, and I've never seen a movie explore this possibility except one, which was Deja Vu with Denzel Washington. But yeah, there's another possibility going back to these squiggly lines is Dmitry Stolnishkov has come up, a Russian theoretical physicist has come up with another possible solution, which is that let's say you go back in time and you assassinate Hitler or try to, you will succeed. But then the universe stops and the universe enters a causal loop like cause and effect, the Star Trek Next Generation episode. And on every iteration of the loop, you get closer and closer to failing until you fail and the universe resumes on the original timeline. So in the example of Polchinski's paradox is you will succeed. you can succeed and knock the ball. It knocked the ball into itself in the past, prevent it from going through the wormhole, but then you have created a paradox. The universe will immediately erase the paradox by putting you into a time loop where in every iteration of the loop, you get closer to failing. So in every iteration of the loop, the air molecules move in a way to blow, the billiard ball out of the way, or your gun jams and you don't kill Hitler on the left. And the scary thing is you wouldn't remember any of the loops. If this is real, this is just a mathematical construct, and you would only remember failing. And so in the end, this really isn't different from Novikov's self-consistency. Basically, you wouldn't remember any of the iterations of the loop, and you would just remember failing to alter the past. So these are all the different possibilities. And of course, in Calvin and Hobbes, which is another fandom, I'm part of. There's lots of talk of time travel, and there's the cardboard box, Calvin's famous time machine, which brings us to another paradox where I'm pretty sure nobody has a solution to, which is the ontological paradox or the bootstrap paradox. So even if you had a solution for the grandfather paradox through quantum mechanical trickery or time loops or some such thing, what happens if there's an information, or even worse, a physical item that has no origin? So in the case of Calvin and Hobbes, Calvin time travels to the future to steal his homework from himself so he doesn't have to do it. Classic, right? But then who wrote the homework originally? Right? Multiverse it helps, but it doesn't quite save you. So these are some of the logical conundrums that space travel doesn't create, but time travel. Multiverse, as I said, solves some of the problems. If there's some bubble universes or multiple parallel universes out there, like in the comics or in Star Trek, of course, that might help. Now, I mentioned one of the solutions to the paradoxes other than multiverse is this quantum mechanical solution I mentioned, where you kill your grandfather and you're simultaneously dead and alive. So one analogy for that is a Mobius strip. I often love making Mobius strips just for fun. The Klein bottles, that's another fun geometric construct. The Mobius strip, if you've ever encountered this, is very easy to make. It has only one side. So if you start drawing, you end up in the same place. So the idea with the Mobius strip analogy is, let's say you did change the past successfully. Maybe you would twist the universe into a Mobius strip where there's still only one universe. Mobius strip only has one side, but there are two timelines that are coexisting where you both did succeed in killing your grandfather and you didn't. Both have. So it's very strange. The gravitational time dilation, though, that might make some time travel possible, or something like the slingshot effect, but to the future, we know it's real because it was demonstrated during a solar eclipse in 1916, I believe it was, by Sir Arthur Eddington. So we know that not only Einstein's special theory of relativity is correct, but also his general theory of relativity as well. So you can think of objects like the Earth, even, and the sun, anything with mass or anything with energy as well, even photons, will produce a gravitational force that you can visualize as a bending of this two-dimensional sheet, which is just a representation of our three-dimensional universe. So time travel comes up again and again. There's Star Trek, the 2009 reboot, Twilight Zone, The Flash on CW, and one of my favorite shows other than Star Trek. I watched all 3 seasons of it. It's only 66 episodes. It got killed before its time, just like the original Star Trek series. I don't know. I've never met another human being who's ever watched a single episode of this show. I hope somebody on the Zoom call has, but there's this really great show called 7 Days. I recently rewatched the whole thing because I found all of the episodes illegally on YouTube. Oh, I shouldn't say that because it's being recorded. Oh, well. Okay. It's fine. So You may have also, on the time travel front, read of a relatively recent discovery, not too recent, we're 2017, of time crystals. And before you get too excited, these are not crystals that you put in your time machine like in Napoleon Dynamite and it makes the time machine work. This is a different state of matter that's periodic in time, not just in space. So we think of crystals as periodic in space, right? They have shape, 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 shape. They have different planes, and they'll have, cube, rhombus, or something like that. And time crystals are objects that have a periodicity in time. It has nothing to do with time travel, but I just think it's really cool. Now, is there any real life evidence we've had time travel? Not really. There's this famous picture of a woman, looks like she's talking into a cell phone. And these things are easy to debunk, though, because who the hell is she talking to? There are no cell towers. And I always bring this up when people use these things. I'm like, there's nobody to talk to. Like, it just, like, even if you had your fancy technology, who are you talking to? Are you calling your people in the future? It just doesn't make sense. So this was probably a woman holding a hearing aid, actually. But my wife came across this. This sculptor looks a lot like the doctor. I don't know. And then there's this composer, Gustav Mahler, who looks a lot like me, at least when I'm wearing glasses. So maybe I'm a time. Who knows? Maybe I can't tell you. So I do disagree with these two famous scientists, Stephen Hawking, who did unfortunately recently pass away, and Neil deGrasse Tyson, because I think the lack of tourists from the future does not disprove time travel. Because one thing I haven't told you yet is that every single way of time travel, even if they work, you can't go back the day before you built the machine. And so in the city on the edge of forever, the Guardian of Forever would only work if, again, if it was like a real thing, like a wormhole or some Stargate. It would only work if it was older than the point in the past you want to go to. So basically what this means, unfortunately, that unless there's a naturally occurring phenomenon in the universe that's billions of years old, if we invented time travel, let's say today, we still can't go back to ancient Greece and Rome. It's too late. Like, anybody can come from the future back to that time. You can't go back the day before you built the machine or you punched the wormhole through space. That is one thing that is shared. It's a shared drawback. But as a result of that drawback, it's easy to debunk the idea that, time travel doesn't exist, because if it did, we'd be overrun by tourists from the future. False. Then I also have another way around it, but it's kind of a cop-out. And my cop-out answer is, the tourists from the future are here. They're not here because we're in the prime time. They're in the altered timeline. But of course, that's a cop-out. So I do hope that there is a future left. And maybe the reason why we don't have tourists in the future, because humanity doesn't have a future. But I'm a Star Trek fan, so I'm optimistic that we'll get through the 21st century. In conclusion, so now I'm going to go through my couple of concluding slides. Oh, and up here, this is a photo. This is an actual picture of me. There's a green screen just for changing the background, but I'm literally sitting with William Shatner there. So actually, William Shatner and I are in the same movie. So this isn't just me meeting him on a convention. William Shatner and I are in the same movie, A Tear in the Sky. So you can go and download and watch it. It's a UFO documentary, actually. It's a little kooky. It's a little sensationalist. So I was slightly grateful, actually, that it didn't go viral and become too popular. Again, I'm being recorded, so I shouldn't say that for the YouTube video. But basically, that's me sitting across the desk from William Shatner. Now, our scene got cut, unfortunately. So you're going to see the movie. You're going to see me. You see William Shatner. You're not going to see us together. This scene got cut, sadly, but pretty awesome. And as you all know, I'm sure Shatner's getting up there in years. And my wife said to me, "Hey, wouldn't it be awesome if William Shatner died soon?" And I'm like, "What? No, of course it's not awesome." She goes, "But imagine if you are the last person to share a filmography with him on IMDb." And I'm like, "Wow, that's a good point." But no, he's been a whole bunch of things since then. So wrapping up the time travel bit, based on our current understanding, we would need faster than light travel. We'd need something with infinite length. We'd need negative energy or infinite energy, infinite positive energy. And so I conclude that while it's not impossible, it's unlikely that a human being will ever travel into the past the way the way we see in science fiction with an on-off button with a switch. I am optimistic, however, that in the next 100 or so years, we'll figure out how to send a subatomic particle back in time a tiny fraction of a second. On space travel, I'm even more optimistic because we need to differentiate between impossible physics versus clever engineering. We don't know what's impossible yet for space or time travel without a theory of everything that marries quantum mechanics and general relativity. So now my money is on clever engineering. If we were to do warp drive, something faster than light, I think we're clever apes and we will figure it out, maybe soon even. But I think it will be much easier to travel slower than light and capitalize on time dilation. So with that, I will conclude, and I'll be very happy to answer any questions.
Thank you very much. That was absolutely fascinating, and my mind is blown. Really, really appreciate you talking with our group tonight. If anybody has any questions, please go ahead and raise your hand, and we'll get you on, and you'd have to unmute yourself as well. Anybody have any questions? I know there's some physicists in the group here. All right, last call if anybody has a question.
I just want to say I'm still absorbing all of this and it's amazing, and I'm going to rewatch it on YouTube so I can pause it and consider all of the things. I feel like I've been fire hosed with an amazing presentation, and I just want to thank you all, Captain Barb for putting it on, and for the presenter. This has been amazing.
Yeah, I have to agree with you on that. I'm sort of in a daze with all this incredible information. I am not a physicist, so I'm going to have to go back and rewatch it myself and do a lot of pausing and absorb and probably look some things up. But yeah, it was great. It was great. Anybody else?
Oh, we have our first question.
Yes, Yolanda.
I'm kind of curious your thoughts on the time dilation concept that they came up with, starting with Star Trek: The Next Generation's Vendetta book. That the faster you get to warp 10, the more time dilates without you actually achieving warp 10.
Yeah, I read Vendetta. I think it's an homage to the real life aspect where if you approach the speed of light, that time dilation occurs. So it's a nice homage to that real physics. I mean, I would believe that faster than I'd believe that warp 10 turns you into a lungfish or whatever it was that Paris and Janeway turned into. Salamander, yeah, whatever the heck it was. I do like how they called back to that on Lower Decks and made fun of that because that was ridiculous. But I appreciate your question. Thank you.
Uh-huh.
Anybody else have any questions?
Barb, I'm sure you must have a question. You are the fearless leader.
I'm just dazed. I'm just dazed. I took a year of physics in college, and I was dazed in that class too. It's one of those subjects that I so want to wrap my head around, but there's something blocking the brain signals that I just want to learn it so bad, and I really struggle with that. This subject, chemistry, those two subjects are really difficult for me, and it's like I'm just on the edge of understanding. I just got to figure out a way to push myself to cross that line.
Well, one thing I can tell you that I think will be very helpful to the whole group here is soon, relatively soon, maybe in a year, maybe next summer, but definitely it's happening. I'm going to be teaching an online class on exotic propulsion, and it's basically going to be almost the same material as this, but broken down into chunks where it's 3 hours once a week for 6 or 8 weeks or something like that, and broken down and gone through slowly. And I think
Nice.
that people might in this group might really enjoy that, and going through everything and learning it all step by step over a multi-week period. So that will possibly be happening next summer. It's definitely happening sometime between this coming fall and next summer. I'm still sorting things out, but I'll be teaching an online class. It's not a real class. You don't need to be like a student in my university. So I call it a class, but it's not like accredited or anything like that. Like anybody can come. I am doing it through though a particular institute that does charge money, so it's not going to be free, but it's going to be, I'm sure, a low, reasonable cost. It's being put on by a nonprofit foundation, and they've got to make money, right? Not profit, but they got to pay their people, who arrange all the virtual classroom stuff. So it's all going to a good cause, and so I do hope people will consider it.
Yeah, how would we, what's the best way to find out when that's available? I mean, I can keep, checking on the website or.
Oh no, I would let you know. I would let you know as soon as it exists. I'll just send you an email. But it might be a few months from now where suddenly you hear from me again. I'll say, "Hey, remember me? And remember my talk?" But yeah, I'll be certain to look you up and email you, so you don't have to do anything.
That would be fantastic. I'm sure there will be several people that would be interested in that. All right, if there's no other questions, I'll scroll through the list here. If there's no other questions, we will wrap up for tonight. Before we go, I'd like to just give a plug for our next two Sol Speaker series. On August 15th, we're going to have a talk by Phyllis Fiello, who is with the Johnson Space Center, and she's going to talk about physiology and space exploration. And then on September 19th, we have a talk on the Artemis project, From Earth to the Moon, and that's by Sharif Gachel, who is an analog astronaut. And if you don't know what an analog astronaut is, it's basically someone who participates in simulated space missions on Earth to help prepare for future crewed space exploration. I had to look that one up myself. So, Dr. Szydagis, thank you so much for the presentation tonight. I know everyone probably thoroughly enjoyed it, as you can see by the chats we're getting in. I wish you all the best with all of your wonderful research, and definitely everybody check out his TED Talk. It's extraordinary. So have a good night, everyone, and thank you again, Dr. Szydagis.
Thank you. Good night.
Good night.
Have a good night.